HCF and LCM of 3 or more integers. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already mastered. In our previous lessons, we focused our attention on finding the highest common factor, or HCF, and the least common multiple, or LCM, specifically when dealing with just two positive integers. You should all feel quite comfortable with that process. However, as we move into more advanced mathematics and encounter real-world problems, the complexity increases. We often find ourselves in situations where we aren't just comparing two numbers, but 3, 4, or even more. The good news is that the core logic you have already learned does not change. We will continue to rely on the prime factorization method as our primary tool. But, as we will see in the upcoming slides, working with a larger set of numbers requires a much higher level of precision and careful attention to detail to ensure no factor is overlooked. So, let's get started by looking at the specific rules for finding the HCF of a larger group. Finding the HCF of 3 or more integers. First, let's refresh our definition. The HCF of a set of numbers is simply the largest positive integer that can divide every single number in that set without leaving any remainder. So, how do we actually calculate this when the set of numbers gets larger? We use a specific rule. We start by expressing each number as a product of its prime factors. Once you have those prime factorizations, the rule for the HCF is this. You look only for the prime factors that are common to every single number in the group, and then you take the smallest power of each of those common factors. Multiply those smallest powers together, and you have your HCF. To make sure you don't miss any details, let's break this down into a clear 4-step process. Step 1. Begin by finding the prime factorization for every number given in the set. Step 2. Carefully identify which prime factors are common to all the numbers. Be careful here. If a prime factor is missing from even just one number, it cannot be part of your HCF. Step 3. For those common prime factors you've identified, look at their exponents and choose the one with the lowest exponent or the smallest power. And finally, Step 4. Multiply all those lowest powers together. The resulting product is your highest common factor. Now that we've established that we are expanding our scope from two numbers to 3 or more, let's dive into the specific mechanics of finding the highest common factor, or HCF. We will apply this exact logic in the next slide when we look at the LCM, and then see it all in action with a full numerical example shortly. Finding the LCM of 3 or more integers. Now that we have mastered how to find the highest common factor, let's shift our focus to the other side of the coin, finding the least common multiple, or LCM. By definition, the least common multiple is the smallest positive integer that can be divided by every single number in your set without leaving any remainder. To find this for 3 or more numbers, we use a specific rule. Just as we did with the HCF in the previous slide, we must first express each number as a product of its prime factors. However, there is a key difference in how we select those factors. While the HCF required us to look only at common factors with the smallest power, the LCM is much more inclusive. The LCM is the product of the greatest power of every prime factor that appears in any of the factorizations, even if that factor isn't common to all the numbers. To make sure you don't miss anything, let's follow this 4-step process. First, perform the prime factorization for each of your given numbers. Second, create a complete list of all the prime factors that appear in any of those numbers. Don't worry if a factor only appears in one number. If it's there, it goes on your list. Third, for every prime factor you have listed, look back at your factorizations and choose the one with the highest exponent or the greatest power. Finally, multiply all these highest powers together. The resulting product is your LCM. In the next slide, we are going to put this exact process into practice with a real-world logistics example to see how these steps work in action. Comprehensive example. Imagine a real-world scenario. A logistics manager is overseeing 3 different delivery routes. These routes take 12, 18, and 30 minutes respectively. To synchronize his delivery schedules effectively, he needs to determine both the HCF and the LCM of these 3 time intervals. Let's walk through the solution step by step. Step 1 is prime factorization. Before we can apply our rules, we must break each number down into its prime components. For 12, we have 2 times 2 times 3, which we write as 2 to the power of 2 times 3 to the power of 1. For 18, it breaks down into 2 times 3, or 2 to the power of 1, times 3 to the power of 2. And for 30, we have 2 times 3 times 5, which is 2 to the power of 1, times 3 to the power of 1, times 5 to the power of 1. Now let's move to step 2, finding the HCF. Remember our rule from the previous slide? We only look for prime factors that are common to all 3 numbers. Looking at our list, the prime factors present in all 3 sets are 2 and 3. Next, we pick the smallest power for each. For the factor 2, the smallest power is 2 to the power of 1. For the factor 3, the smallest power is 3 to the power of 1. Multiplying these together, 2 to the power of 1 times 3 to the power of 1, gives us an HCF of 6. Finally, let's proceed to step 3, finding the LCM. This time, the rule changes. We must include every prime factor that appears in any of the numbers. In our case, we have 2, 3, and 5 this time. We choose the greatest power for each. The greatest power of 2 present is 2 to the power of 2. The greatest power of 3 is 3 to the power of 2. And the greatest power of 5 is 5 to the power of 1. When we multiply these together, 2 squared times 3 squared times 5, we get 4 times 9 times 5, which results in an LCM of 180. Now that we have covered the theoretical rules for finding the HCF and LCM, let's put them into practice with a comprehensive example. Let's walk through the solution step by step. As we move to the next slide, I want you to pay close attention because there is a common trap regarding the relationship between these results that you'll want to avoid. Important remark: the product relationship. Now, before we wrap up, I want to address a very common point of confusion. Many students, when moving from working with 2 numbers to working with larger sets, try to apply a property they learned previously. As you might remember from our earlier lessons, when we are dealing with just 2 positive integers, let's call them a and b, there is a special identity that always holds true. The highest common factor of a and b, multiplied by the least common multiple of a and b, is exactly equal to the product of a and b. However, I need to give you a crucial warning here. This specific relationship is not applicable when you are dealing with 3 or more integers. For any 3 positive integers, let's call them b and c. The product of the 3 numbers does not equal the product of their HCF and LCM. To make this crystal clear, let's perform a quick verification using the numbers from the example we just worked through in the previous slide. Let a be 12, b be 18, and c be 30. First, let's find the product of the 3 numbers. 12 times 18 times 30 gives us 6,480. Now, let's look at the product of the HCF and LCM we calculated earlier. We found the HCF to be 6 and the LCM to be 180. When we multiply 6 by 180, we get 1,080. As you can see, 6,480 is clearly not equal to 1,080. This proves that the rule we use for 2 numbers simply breaks down when a third number is introduced. Keep this in mind as we move into our final summary. Key takeaways. All right, we have covered a lot of ground today. So let's pause and summarize the key takeaways to ensure everything is clear before we move on to the common pitfalls to avoid. First, let's recap how to handle the highest common factor for 3 or more numbers. Remember, when you are looking at a set of 3 or more integers, the HCF is the product of the smallest power of only those prime factors that are common to every single number in the set. If a prime factor isn't present in all of them, it doesn't make the cut for the HCF. Next, for the least common multiple of 3 or more numbers, the rule changes slightly. Here, you are looking for the product of the greatest power of every prime factor that appears in any of the factorizations. You aren't just looking at common factors here, you are looking at all of them, but you must always choose the highest exponent. Finally, I want to reiterate a very important warning from our previous slide regarding the product relationship. Please do not fall into the trap of assuming that the HCF multiplied by the LCM equals the product of the numbers. That specific identity, where HCF of NB multiplied by the LCM of NB equals a times B, works strictly for two numbers. As we demonstrated with our delivery route example, this rule fails when you introduce a third or fourth number into the set. Keep these 3 points in mind, as they are the foundation for solving more complex problems. Now, let's look at some specific mistakes that students often make so you can avoid them in your exams. Common mistakes. Now, as we wrap up this lesson, I want to pause and highlight some common pitfalls. Even if you understand the core concepts, these 3 mistakes can easily lead to incorrect answers during an exam. First, watch out for including non-common factors in your HCF. It is very common to see students include a prime factor in the HCF calculation simply because it appears in 2 of the numbers. However, remember what we discussed in slide 2. For the highest common factor, that prime factor must be present in every single number in the set. If it's missing from even one number, it cannot be part of the HCF. Second, be careful not to use the smallest power when calculating the LCM. It is easy to get the 2 rules mixed up because they look so similar. To keep them straight, use this mental shortcut. For HCF, think smallest power of common factors, but for LCM, you must use the greatest power of all factors involved. Finally, and perhaps most importantly, do not try to apply the product formula to 3 numbers. As we saw in our important remark on slide 5, the rule where the HCF multiplied by the LCM equals the product of the numbers only works for 2 integers. Many students mistakenly try to find the LCM of 3 numbers by dividing the product of all 3 numbers by their HCF. As our example with 12, 18, and 30 proved, this will lead you to a much larger, incorrect answer. Always stick to the prime factorization method to ensure accuracy.